Hello, everyone. We are going to start in a couple of minutes, just to give some time to people to connect. You can all hear me okay? Thank you.
Yep.
Bandy, that's the right attitude. Good morning, lovely people. The way to beat Corona. Okay, the numbers seem to have stabilized during the last minute, so I guess we can start. So let me share my screen with you. That would be this one, I believe. Okay, you can see my slides, right?
Yeah.
Good. So what's the plan? The plan is, excuse me, the plan is we're going to do an extremely clever algorithm for finding a mean cut in a graph in a fast way, which exemplifies several ideas used in designing randomized algorithms, but it's also an important algorithm because several problems, in fact, require you to find minimal cuts, for example, as we will see in clustering. So, and after we finish today, Karger, we are moving to the famous PageRank, which students always find very interesting. And we are going to give a very detailed intuition that these two guys, Page and Brim, employed to design this algorithm that made them so incredibly rich. And hopefully that will demonstrate that knowing just the very basics of randomized algorithm can have huge impact in your engineering practice. So what is Karger's min-cut algorithm? So assume that you are given an undirected, connected, weighted graph G with vertices V and edges E, and with weights of all the edges positive reals, right? So just like in min-cut max flow, what is a cut in a graph? Well, it's any partition of the set of vertices V into two non-empty and disjoint subsets, X and Y, so such that X union Y is the whole set of vertices. So every vertex has to belong either to X or to Y, but not to both. Because the graph is undirected, the capacity of a graph, of a cut in G is the total sum of weights of all edges which have one end in X and the other in Y. You remember when we did capacity of a cut in directed graphs, we only counted the capacities of edges that go from the source side to the sink side. But here we don't have two distinct vertices, source and sink, and the capacity of the cut, because the edges are not directed, is simply the sum total of capacities of all edges that cross the cut. So one of the vertices is in X and the other vertex of the edge is in Y. So you can see it here on the picture, the dashed line representing the cut, and the capacity of the cut T is simply sum of the weights of all edges, so that U is in X and V is in Y. And what you are interested is to find a cut so that the total capacity of all the edges that cross the cut is as small as possible. What would be one example? Why would you need to do that? Well, assume that the weight of an edge U and V is the degree of similarity of the vertices U and V. So we assume that the vertices are some points in a population and that we have some notion of similarity. For example, the reciprocal of the Euclidean distance between these two vertices. And you would like to cluster the universe, all the points into two clusters, so that the similarity between the clusters is as small as possible. So you want to minimize the sum total of similarities between vertices that belong to different clusters, right? And the degree of similarity would be, of course, sum total of similarities of each pair. So this is a very natural problem to consider. We will get back to clustering and cuts in clustering later. So we say that an edge belongs to a cut if it crosses the cut, right? If one vertex is in X and the other is in Y. So the task is, given a connected graph, find a cut of minimal possible capacity. So let's see how we might solve this problem. Well, you know how to find mean cut in directed graphs. So you can simply replace every edge. Since G is undirected, we can replace every edge in G with two directed edges in opposite directions. In such a flow network, this cut would also be the smallest capacity cut with X as the source and Y is as the sink if X belongs to X and Y belongs to Y. So what you could conceivably do is you can say fix, you can go through all possible pairs of vertices, taking one as a source and the other as the sink, and find max flow, and from max flow deduce the capacity of the mean cut, and then find the minimal cut for all possible distinct pairs of source and sink. Now, actually, it's easy to see that you can fix the source and just vary with the sink all over the other vertices. Why? Well, because the graph is completely symmetric, right? For every edge in one direction, there is an edge in the opposite direction. So max flow from your source to sink is exactly the same as max flow if you reverse the direction of all flows if you make the sink now a source and the source the sink and just replace the direction of the flow with the flow in opposite direction, you will get exactly the same amount of flow by symmetry. So this means that since it's not important who is source, who is sink, you can fix one vertex and then arrange with the other end over the rest of the graph. So you will have in this way n-1 possibilities for the sink, and the fastest max flow algorithm that we have today is runs in time V cube. So the cube of the number of vertices. So since you also have to vary the sink, this obviously would produce an algorithm that runs in time n to the fourth, right? Because so the idea would be you fix one point and then arrange with, and you call it source, and then arrange with t through all possible n-1 vertices. For each choice of the sink, you can run max flow algorithm to find the mean cut, and each run costs you V cube, but you have n-1 choices for the sink. So in total, you will have V cube, O of V cube times V minus 1. And of course, this is O of V to the fourth power, which is extremely slow because in practical applications, the graphs that we are looking for the mean cut tend to be very large, have the vertices in the order of thousands, if not more. Okay, so we want to find a faster way to find a mean cut in undirected graphs. How do we do that? Well, the trick is to use randomization, and the idea is, as we will present this famous algorithm, the Karger mean cut algorithm, we will present it in two stages. In the second stage, we will refine the construction of the algorithm that we will design in the first stage. And the main idea is actually amazingly simple. And okay, so here is a question. Wouldn't we have to do it for all sources as well, so that the complexity is v to the 5? Actually, v to the 4th suffices, and this is the idea. The idea is, consider this mean cut. Then for every, because both sides are non-empty, you can pick any point on the left as a source and any point on the right as sink. And actually there is no left and right, because, as I said, the max flow from one point to another, one vertex to another, is exactly the same as max flow if you actually switch the role of the sink and the source, because for every edge in one direction, you have an edge in the opposite direction, so you can reverse all the flows. So then this means that the source can be an arbitrary point, because it will definitely belong to one of the sides of the partition. So it's enough to fix the source and then arrange with the sink through all other points. You can persuade yourself that this is correct because of this symmetry, because the graph is undirected. Okay, very good. So now, what is the basic operation of the Karger's algorithm? Also, what I wanted to say is, I admire not only the cleverness of this brilliant algorithm, but also the bravery of the idea, because the basic construction is extraordinarily simple, and it works with an extremely small probability. But Karger found a way to do a trick which is often used in randomized algorithms design, that can be called amplification of the probability, namely altering your algorithm in such a way so that this minuscule probability somehow grows of success, grows fast. So let us see what the basic operation is. The basic operation is this. You contract, you pick an edge, and we will see how you pick an edge, but you pick an arbitrary edge in the graph with vertices u and v, and you contract these two vertices into a single vertex. So now the edge between u and v will disappear, right? Because u and v become one point. And then you update all the edges that were between, so now the edges between x and u and x and v will be replaced by a single edge between x and this joint fused point uv, and you set the capacity of this new edge to be exactly the sum of the capacities of the two edges that get collapsed into a single edge when you merge U and V. So you can just imagine making U and V shorter and shorter, and then these two pipes will get closer and closer until they fuse into a single pipe of the capacity that is equal to the sum of the capacities of the so the question is that max flow runs in time On to the fourth, so N will be always, well, at least in this context, N is just the number of vertices in the graph. So N refers to the number of vertices. Okay, so having in mind this contraction procedure, let us now see if we pick an arbitrary edge, how does this impact the capacity of mean cut? So the question is, does the contracting only apply to edges which cross the cut? No. So we pick edges, we don't know where the mean cut is. So we don't know which edges we might contract or not contract. So we simply randomly, we will see with what probability, we pick a random edge and contract it. It doesn't have to be across the mean cut. It's simply a random edge because we don't know what a mean cut is. Very good questions. It's really much better when the lectures are live because you guys keep me honest. When I forget to specify something, you immediately catch it, rather than having pre-recorded lectures. Okay, so we denote thus obtain graph as GUV. So that's graph G, that's the graph obtained from G by contracting the vertices U and V, and of course eliminating the edges between U and the edge between U and V. So here is the claim. If two vertices U and V belong to the same side of a mean cut, XY, then after collapsing U and V into a single vertex, the capacity of the minimal cut in GUV is exactly the same as the capacity of the minimal cut in G. So here is the picture. So assume that XY partition is, this is maybe one of several, but a minimal cut. And assume that U and V belong to the same side of the partition here, partition is X. Then the claim is that the capacity of the mean cut doesn't change after this contraction. Why is this so? Well, capacity of the mean cut can change only if if the edges that cross the cut change. Because U and V are of the same, on the same side of the cut, the loss of the edge UV does not change the capacity of the mean cut. But now, if you take any point on the opposite side of the cut, then of course the only edges that change are the edges that connect X either with U or NV. But by our procedure, we replace these two edges, one connecting X with U and the other connecting X with V. We change them into a single vertex, and the two edges are replaced by a single edge, but with the capacity that is equal to the sum of capacities of the previous two original edges. So clearly, if you contract this edge disappears, but it doesn't belong to the mean cut. And the two edges that might belong to the mean cut, if they connect U and V with a point X on the opposite side, they will change, but they will be replaced by a single edge, but of exactly the same capacity. So clearly then the sum total of capacities of all edges that cross the mean cut will be exactly the same. So capacity of the mean cut will not change. What happens if the two vertices U and V belong to the opposite side of the minimal cut? Well, as you will see, then what can happen is that the capacity of the mean cut in the resulting graph can only increase. The capacity of the mean cut cannot decrease. So let's see why this is so. So here is, let's see, maybe I have a better picture on the next slide. So here it is. So you have U and V that are on opposite side of the mean cut in G, right? Then we contract them. Now, the mean cut that results might be, this might no longer be the smallest cut because we removed the one edge that crosses the cut. So assume that this partition now is the mean cut in the new graph. Well, notice now the following. If I take this fused vertex and unfuse it, right? If I split U and V back into two vertices, but I keep them in the same side of the mean cut in the collapsed graph, right? I split them into so that they both belong to the same partition. Happens, then you see the capacity of this cut in the collapsed graph is exactly the same as the capacity of this cut, produced cut, in the original graph. So what does this mean? It means for every cut in the collapsed graph, we can produce a cut in the original graph that is of exactly the same capacity. Right? So what is the idea? You fuse the two vertices U and V. You find, you now consider any cut in the thus obtained graph. Then you split back U and V, but keeping them in the same side of the partition as joint vertex belonged. And lo and behold, you produce a cut that is exactly of the same capacity as the cut here. So for every cut in the collapsed graph, there exists a cut in the original graph of exactly the same capacity. So the collection, the total collection of all cuts in the original graph is larger than the collection of cuts in the collapsed graph. But if you have a larger set, right, the capacities here are a subset of all capacities here. So minimum of the set here, right, can be only smaller than the minimum here. So what is, how to think about that? So let's say we record here. So here the vertices will be the numbers that are the capacities of the mean cut. And we know that all the capacities of mean cut in mean cuts in GUV, right, is just a subset of all capacities of mean cuts in G, right? So if you have a collection of numbers, so that, and a subset of these numbers, then the smallest number in the smaller set can be only larger or equal than the smallest number in the original set, because you have extra elements here, and maybe one element here is smaller than all elements in the subset, so the minimum will be smaller. So when you fuse the vertices that of an edge that go across the cut, the capacity of the mean cut in the resulting graph can be only larger or equal than the capacity of the mean cut in the original graph, because we showed that for every cut in the collapsed graph, we can produce a cut in the original graph that is of exactly the same capacity. So the choice of cuts in G is larger than the choice of cuts in GUV, and consequently the smallest element of all in this larger set can be only smaller or equal than the smallest element in the smaller set. So this is just the proof that I just explained to you. Let me see. Okay, so let's go through the algorithm once again, because the argument once again, because you have lots of questions, and it is really a tricky argument. So what are we doing here? We consider the case that vertices U and V belong to the opposite side of the mean cut. And after we fuse the vertices, maybe this partition will no longer be the mean cut in the altered graph, because notice this edge does not belong to the cut, but after fusing, it is added, the capacity of this edge is added to the capacity of that edge, so the capacity across this mean cut increased. So maybe this is no longer mean cut in the new graph. So we now want to show that the capacity of mean cut in the transformed graph can only be larger or equal than the capacity of mean cut in the original graph. How do we do that? Well, we prove that for every cut, not even necessarily mean cut, just for every cut in the new graph, you can construct a cut in the original graph that is of exactly the same capacity. How do we do that? Well, take any cut here, right? And split U and V back into two vertices, but keep them in the same side of the partition where UV was. So you get a picture like this. So now, just as in the previous case argument, the capacity of this cut didn't change, right? Because we only split the capacity of this edge into capacity of two edges. So the capacity of this cut is equal to capacity of that cut. So what does this show? It shows that for every cut in the new graph, there exists a cut of the same capacity in the old graph. So the set of possible capacities of all cuts in the original graph is a superset. It's larger or equal the set of capacities in the new graph, right? And for that reason, because all the capacities available here are also available in the original graph, so minimum of these can only be larger or equal than minimum of these, right? Because you are taking minimum over a larger set, right? This is just what we draw. Where did I draw it? So you have, you have, if you plot the, if you collect here all the numbers that are capacities of the cuts in the original graph, only a subset of them is the capacities of the cuts in the new graph, right? Because we have shown that for every capacity in the new graph, there exists a capacity in the larger graph, there exists a cut of the same capacity in the original graph. So your options for values of capacities of cuts in G are larger than your options for capacities in the collapsed graph. So mean over this set of smaller collection can be only larger or equal than mean over a bigger collection, because maybe there exists here a point that does not belong to the subset and that is smaller than all the points, all the capacities from the subset, right? So this shows the capacity of the mean cut in the collapsed can only increase. Okay, so now, so to summarize, you can persuade yourself by going through the argument at home, but to summarize, if two vertices belong to the same side of a minimal cut, collapsing them will not change the capacity of that minimal cut. If they are from the opposite side of a minimal cut, this cut, after collapsing, might cease to be a mean cut, right? And lo and behold, we just shows the capacity of the mean cut can only increase after the collapse. So what does the algorithm, first attempt of the algorithm do? Well, it says the following: pick an edge to contract with a probability proportional to the weight of that edge. So you take the weights of all edges, right? And you normalize them by dividing them with the sum total of the weights of all edges in the graph. This is clearly a number for every edge. It's a number smaller than 1. So we can interpret it as a probability. So in this way, you make the possibility to pick an edge of large weight more likely than to pick an edge of small weight. then what you do is you contract this edge, and you continue doing that until only one edge is left. And remember, we are assuming that the graph is connected. So at the end, you will be left as you keep going through the graph, contracting. Of course, the graph remains connected. And at the end, you will get a single edge. And the algorithm then takes the capacity of that last edge to be the estimate of the capacity of the minimal cut in G. So it's an amazingly simple algorithm. You pick an edge with probability proportional to the weight of that edge and contract it. Now you have a new graph with the new weights, right? Because one of the weights some of the weights become sums of the weights of two edges, right? But in this new graph, you again pick with probability that is equal to the weight of that edge, and you keep contracting until only one edge is left, and you claim you take the weight of this edge as the capacity of the mean cut. So you are doing a very risky operation of contracting edges, which might increase the capacity of the mean cut, and you just hope for the best. So let's see how optimistic you are that you might have gotten the correct value. So we prove a simple theorem that says the following. Let GUV be the graph obtained from a graph G with n vertices by contracting an edge E from that graph. Then the probability that the capacity of a minimal cut in GUV is larger than the capacity of the minimal cut in G is smaller than 2 over n. So the probability that you mess up, right, the capacity of the mean cut is smaller than 2 over n. Why is this so? Well, as we have shown, the capacity of the mean cut can increase only if the vertices collapsed are on the opposite side of every mean cut in G, right? So we then let M be the mean cut, the minimal capacity cut in G. Then the probability that you messed up, namely that the capacity of the mean cut in the contracted graph is larger than the capacity of the mean cut in the original graph G, is of course smaller or equal than the probability that the edge UV belongs to the mean cut, that it crosses mean cut, because we have shown that the capacity can increase only if you contract an edge that crosses the mean cut, but not always, right? Because you might ruin one mean cut, but another mean cut might remain intact, because there can be several cuts of the same smallest minimal capacity. So here we have inequality. Clearly, because the event on the left happens in some cases of the event on the right, so its probability is smaller or equal than probability of the edge belonging to M. So here, note, we are not going to the very end. Here we are just considering the probability that a single contraction ruins the capacity of the mean cut, right? So we are contracting a single edge EUV, and we want to show that the probability of messing up the capacity in thus obtained graph in which only one edge is collapsed is smaller than 2 over m. So the first step is that we estimate that the probability of messing up things is smaller or equal than the probability that edge belongs to M, which is of course exactly will correspond to the capacity of the mean cut. So let's see now. So what is the probability that an edge belongs to M? Well, this is because we pick the edges according to their weights. Probability to pick an edge that belongs to M is equal to the sum of the weights of all edges that belong to M, because we just have to pick one edge that belongs to M. Probability to pick one element given the probabilities of the probabilities of picking one element is just the sum of the probabilities, right? Because these are disjoint events. Divided by the sum total of weights in all edges, right? Because you pick an edge in M with probability equal to the sum of the weights proportional to the sum of the weights of the edges that cross M. So now, the claim is that in any graph, you have the following property. Twice the sum of the weights of all edges in the graph is sum over all vertices V that belong to the graph of sums over all edges whose one end is V that belong to E. So here, what are we doing? We are doing the following. We are summing up. We go through all possible. Vertices, and for every vertex V, we sum up all the weights of all edges that are incident to V. And then we sum these sums. So for every vertex, we sum the weights of all edges that emanate from V, and then we sum over all vertices. Why do we get precisely twice the weight of all edges in the graph? Because we count every edge twice, exactly. Right? You will count this edge once for V and once for its other end. So this sum here, in this sum here, every edge is counted twice, once for one end and once for the other end. So you get twice the total. Okay, so now the claim is if you fix V and you sum the weights of all edges, so now V is fixed and we again sum the weights of all edges that are incident to V. The claim is that the sum of these weights must be bigger or equal than mean cut capacity of G. Why is this so? Why is it the case that if I pick any vertex V and sum up the capacities of all edges, I have to get a number that is larger or equal than mean cut capacity. So mean cut is the capacity of the smallest total capacity cut in all, among all cuts in G. Can you think of a cut whose capacity is precisely the left-hand side? So is there a cut whose capacity is precisely the sum of the capacities of all edges that emanate from V? Exactly. Here it is. James says, take V as one side of the cut and all other vertices put in the other side of the cut. Well, then clearly capacity of this cut, very unbalanced cut, will be exactly sum of the capacities of the edges emanating from V. So we have this inequality. So now, what we can conclude is, if now assume that I sum up all these inequalities for all vertices V. So if I sum over all vertices V, then I'll get precisely this expression on the left. If I sum up inequalities, one inequality for each vertex V. So if I sum them up on the left, I'll get precisely this, which we know is equal to that. And on the right-hand side, I will get mean cut repeated as many times as we have inequalities. But the number of inequalities is equal to the number of vertices V. Because for each vertex V, we get one inequality and then we sum them up. So this means that this sum, which is equal to that, is n times mean cut. So if I divide by 2 both sides, right? So if you ignore these 2 here and put it here, then this 2 times VE is precisely this. And on the right-hand side, we have n times mean cut capacity G. So if I divide by 2, I get that the sum of all weights in the of the edges in the graph is larger or equal than n times mean cut capacity. So you see, these are all very crude estimates. You know, it's very, very simple algorithm and simple calculation. So what do we have now? Remember, probability to choose an edge that goes across the cut is equal sum of probabilities across the cut over sum of the weights across the cut divided by sum total of all weights. But we just saw that this sum, right, is the capacity of the mean cut, because we sum up the weights of all edges that cross the mean cut. And on the bottom, we get something that is smaller or equal, right, than n over 2 times the mean cut capacity. So because if you see here, mean cut, so sum of all the weights is larger than n over 2 times mean cut capacity of G. So you get this estimate. So we are replacing this on the bottom with n over 2 times mean cut, mean cut capacity of G. And now I can cancel out mean cut capacity of G on top. and mean cut capacity on the bottom and get 2 over n as we claimed, right? Okay, so just from this inequality, right, we are replacing this with n times mean cut capacity G, and we get this. Okay, so we proved that the probability to mess up after single contraction is 2 over n. So if we continue this process, right, if you continue this process, we have to estimate the probability to end up with a correct mean cut. And the algorithm says if we run edge contraction procedure until we get a single edge, then the probability pi that the capacity of that final edge is equal to the capacity of a minimal cut in G is of the order 1 over n squared. So let's see why this is so. Well, we just saw that as you keep contracting, you get that probability of messing up things is not larger, it's smaller than 2 divided by the number of vertices in the original graph. So this is the capacity, so 2 over n is probability that you will mess up. Then 1 minus 2 to the n is the probability that after the first contraction, the capacity of the mean cut will be the same. In fact, so the probability of the mess up that we obtained is independent on the edge weight. It can be estimated exclusively in terms of the number of vertices. And that's an extremely interesting observation, that you can have a estimate of the probability that the mean cut will be surviving independent on the capacity of the mean cut, which is kind of somewhat counterintuitive, right? Because the probability of fusing things that belong to opposite sides of the mean cut does depend on the capacity of the mean cut. But you can, just by these rough estimates, you can produce also a bound that is independent on the weights. So this is the probability that the capacity of mean cut will survive. By the way, at the very edge, when you get one single edge, what's the capacity of the mean cut? Well, the capacity of the mean cut is precisely the capacity of this single edge, because the mean cut is 1 point on one side and the other on the other side. So then you got a graph with n minus 1 vertices, and capacity, the probability that after you contract 2 vertices from that graph, you don't injure the capacity of the mean cut is 1 minus 2 divided by n minus 1. In the third graph will be 1 minus 2 divided by n minus 2, all the way till the end. When you have just 3 vertices, the probability of not injuring mean cut is 1 minus 2/3. And now, if you just put these numbers as a single fraction, right, by just multiplying 1 with the denominator, right, you get n minus 2 divided by n times n minus 3 divided by n minus 1, n minus 4 divided by n minus 2, n minus 5 divided by n minus 3, and so forth. So notice this n over 2 can cancel out this n over 2 here. This n over 3 here can cancel out n over 3 here. And so forth. At the very end, you will be left only with the last two numbers on top and the first two numbers on the bottom, because all of these, right, will cancel out. So you get 2 times 1 is 2 divided by n times n minus 1, which implies the claim of the theorem. So probability not to mess up things is larger or equal than 1 over n squared. Now, that is a pathetic probability. Why? Well, if you have a graph with, say, 10,000 edges, probability will be 1 in 100 million, right? Which is essentially would never happen. And this is the point where I am amazed that Karger didn't give it up, right? Because it looks like a pathetic, unlikely event that things will not be messed up. But victory belongs to the brave. Notice that if you run the construction not until you get a single edge, but until you contract half of the edges. Sorry, not half of the edges, but in each contraction you lose one vertex, right? The number of vertices in the graph drops by 1. You stop when you reach n over 2 vertices. When you reach n over 2 vertices, let's see what is the probability. Well, again, you have exactly the same expression, but you stop when you reach n over 2 many vertices. Now you do the same trick. Everything cancels out except so this will cancel out with this. So this will, sorry, let me erase this. So this will cancel out this will cancel out this, and so forth. So you are left with n times n minus 1, just as before. But now, instead of going to 1 times 2, you stop. So this will cancel this, and then this will cancel that. So only, again, the last two are left. But the last two are n over 2 minus 1 times n over 2 minus 2. So what is this? This is on top, you get something of the order of n squared divided by 4. On the bottom, it's of the order n squared. So this is 1/4. So notice, things go bad only when the graph gets small. When you are doing it only for large graphs, and you stop when you contract half of the vertices, right? When you lose half of the vertices, if you stop there, the probability of success that you didn't mess up is actually quite large. And it is it's bigger or equal than 1/4. And that's very different than what we had 1 over n squared. Because this 1/4 can be amplified. And that's the trick. So the algorithm is amazingly simple. You pick the edges according with probability proportional to their weight. You contract the two endpoints of the edge, and you keep doing that until you end up with only n over 2 vertices. In each construction, you get a graph with one vertex less. And lo and behold, this simple calculation with very rough estimates shows that probability of success is actually 1/4. But you are not home yet because you need that single edge. But the idea is now you compensate for the loss of probability, namely that probability got to be only 1/4, by repeating the whole experiment 4 times. So this is what you do. This is the algorithm. Before we read the algorithm, let me show you the picture. Here it is. So this is your original graph with n vertices. You perform this partial contraction until you reach a graph with n/2 vertices. This is a randomized procedure. Then you repeat the very same procedure, which is a randomized procedure, which will give you a different graph because you will make different random choices which edges to contract, also of size n/2. And you do it 4 times. And the idea is probability that you haven't messed up in one of the vertices is 1/4, but you have 4 of them. And the fact that you have 4 of them will compensate for the drop in probability. And you keep doing that. Now you contract a graph with n/2 vertices into a graph with n/4 vertices, but you again do it 4 times, right? With running 4 times this partial contraction randomized procedure. And you keep doing that all the way to the bottom. Everywhere you will get single edges, and you take minimal capacity of these single edges as an estimate of your mean cut. So this is the brilliant construction. Yes, as you run partial construction, you suffer loss, 3/4 of loss of certainty, right? You end up with a graph that is okay with probability only 1/4. But you repeat your algorithms 4 times. And then you hope that with very high probability, at least one of the branches will result in a correct edge with the correct weight, that there will be at least one branch that will contain no errors whatsoever. So this is, let's go back and look at the algorithm. So algorithm is very simple. You start with your graph, okay? Then, while you have more than 2 vertices, you run 4 times the randomized edge contraction algorithm until you get a graph with only half number of vertices, and you run it 4 times. And you denote by GI, where I goes from 1 to 4, the resulting graph. Then you recursively call the very same algorithm we are defining on all 4 graphs. And then you return the smallest capacity among the capacities of all thus produced single edges at the very end. Right? So, and this is exactly what we described here. Your graph has n vertices. Run your algorithm to produce a graph with only n/2 vertices, but run it 4 times. Because it's a randomized algorithm, you will likely produce 4 different graphs. Probability that the mean cut is correct in one in each of these graphs is one plotter, but there are 4 of them. So it's kind of reasonable to assume that if you keep doing that, at the very end, at least one branch will be correct, will produce the correct mean cut. So let's see now what is the runtime of the algorithm, because this looks like it involves a lot of runs of the basic algorithm. So we have to make sure that they don't add up excessively. What's the runtime? Well, your original algorithm has been reduced to 4 instances of the algorithm to run your algorithm on graphs of size n/2. And the contraction, of course, takes O of n squared operation, right? Because when you update your graph, after you contract vertices, you have to inspect all the edges, and the edges that that are affected by contraction, right? You have to update their capacities by summing the capacities of the edges connecting to the both ends. So this is clearly, you have at most n squared pairs of vertices to consider whether the edge has to be updated or not. So the runtime is this. And the master theorem, so what is the case? This is n to the log b of a is the critical polynomial, which is n log 2, right, of 4, which is n squared. So the critical polynomial is of exactly the same growth rate as the overhead. So this is the second of master theorem. So T of n will be then O of n squared log n. Okay. Remember, the deterministic algorithm for mean cut, the best one would run in n to the 4th. And n squared times log n is just huge. It's orders of magnitude better, right? If n is large. So this algorithm remains fast despite a lot of recursive calls, iterative calls. So this is the runtime, but what's the probability now that one of the branches did not get injured, that it preserved the correct mean cut capacity? This is what we have to estimate. So let's see how we do that. Probability of success for a graph of size n is equal to 1 minus probability of failure on all 4 branches, right? So if all 4 branches return a larger mean cut than the true mean cut, then that's the failure. But what is this? This is 1 minus, and probability of failure on all 4 branches is probability of failure on 1 branch taken to the 4th power, right? But this is now, we replace probability of failure again with the probability of success, right? So this is 1 minus, and then this inside is 1 minus probability of success on 1 branch to the 4th power. This is, now when do you succeed on 1 branch? Well, probability, in order to succeed on 1 branch, you have to succeed in doing the partial, right? So let's see in the previous plot. So in order to succeed on this branch, what has to happen is you have to survive getting to this point without injuring the cat. Probability is 1/4 times probability of success on a branch of this node. So in total, this is 1/4. So this is to survive contraction up to n/2. And then probability for the rest of the algorithm to survive for the graph of size n/2. Okay, so to simplify notation, we will denote P of n, the probability of success for a graph of size n. Then we have that P of n, which is this, is equal 1 minus 1/4 probability for the size n/2 taken to the power 4. And then a little bit of algebra. If you take this to the 4th power, this is what you get. Oh gosh, why is it doing this? Okay, so you get this expression just by taking by hand this to the 4th power. And then notice, P is a probability, so it's smaller than 1. So this guy here is larger than this guy here, right? Because it's 1/16 and here is 1/256. And here P of n/2 is taken to the 3rd power and P is smaller than 1. So Q to cube is larger than Q to the 4th if Q is smaller than 1. So if I drop, so the contribution of this part is positive because this is larger than that. So if I drop it, the things become only smaller and you get P of n/2 minus 3/8 P of n/2 squared. Now, by induction, and this is where a little bit of magic comes, Clever Karger showed that a solution to this strange recurrence inequality is satisfied by if that P of n P of n has to be larger than 1/log n. So if P satisfies this recursion, then the claim P of n must be larger than 1/log n. We prove this by this fast induction, right, in which you progress by doubling or you regress, right, by dividing by 2. So we assume that the assumption is true for n/2, right? And then we show that in this case, it's also true for n. Okay. So what happens? Well, we have this inequality. By assumption, this is smaller than, this is larger, right, than 1/log n/2. So we get that this is larger than so this is larger than 1/log n/2 by assumption, minus 3/8 divided by log n/2 squared. Now, n/2 can go out, and you get here, this will be log n minus log 2 of 2, which is minus 1, and this is log n minus 1 squared. And then you use the following inequality, that 1/x minus 1 minus 3/8 x minus 1 squared is larger than 1/x. To prove this, you can move 1/x to the other side of inequality and show that this is a monotonically increasing function, and you can just plot it and see that for all x that are larger than 8/5, in fact, this inequality holds, so this expression is larger than 1 over log n because of this inequality, right? So the possibility of failure of the new algorithm is 1 over log n. Remember, possibility of failure of the original algorithm when we contracted all the vertices until we got only 2 was 1 over n squared. So Karger managed to boost the probability by refining algorithm from 1 over n squared to 1 over a log n. And here it's crucial that the probability decays only as log n, because the final algorithm will now be as follows, right? So yet another refinement. We will run this 4-contract algorithm log n squared many times. What is the probability of the success? Well, probability of the success is 1 minus probability of failure taken to the number of runs, because you have to fail in each run, which is log n squared. But now you can represent this, you can use that 1 minus 1 over k to the power k is 1 over e, right? That's what we mentioned last time. And lo and behold, you get that this is, so you can write this as 1 minus 1 over log n to the power log n, and then the whole thing to the power log n. Let me just be a little bit more economical. So for you to see what's happening, we will write this as 1 minus 1 over log n to the power log n, and then the whole thing to the power log n. So when n grows, log n also grows. So this inside is converges to 1 over e. So you have that this probability is 1 minus e to the power minus log n, or 1 minus 1 over e to the log n, which ends up as 1 minus 1 over n. So if you run your algorithm, this 4-contract algorithm, log n squared many times, the probability of success is huge. It's 1 minus 1 over n. So if you have 10,000 vertices in your graph, the probability of success is 1 minus 1 over 10,000, which is guaranteed success almost, right? What is the total runtime of our algorithm? Well, the 4-contract algorithm runs in time n squared log n, and we run it log n squared many times. So the total run times is n squared log n cube, but log n cube is very small compared to n squared, right? So this is much, much smaller than n over n to the 4th power. So in fact, the algorithms that find mean cut all use this brilliant Karger algorithm. Now, what you have to do is read very carefully these notes. Now, this looks intimidating. Who would come up with this algorithm? Well, in this course, right, we cannot afford to deal with kind of simple or moderately complicated problems that we did in 3121 when we practiced problem solving skills. Here, we are learning sophisticated techniques and sophisticated algorithms that are used in practice. And Karger got famous for this, this algorithm. So you can learn the best from the masters. So trace every step of the algorithm and try to figure out the reasoning behind it. So the reasoning behind it was always this boosting of the probability. You have one very basic algorithm, the first one that we saw that goes all the way to a single edge. And the probability of success was minuscule. It was 1 over n squared. Then what Karger did, he amplified this probability to probability 1 over log n, which is much better, but still small. If n is large, 1 over log n is no longer right. It's very small. 1 over log n is much better than 1 over n squared. It's much larger than 1 over n squared, but it is still prohibitively low, right? It's just so if n is 2 to the power, say 20, right? Probability of success is only 1 over 20. And if n is much larger, then it becomes smaller and smaller. So first amplification was from probability 1 over n squared to probability 1 over log n. How did he do that? Well, he realized that the simple algorithm misbehaved when n dropped, when the size of the graph dropped below n over 2. To reach point n over 2, probability of success was large. It was 1/4. So to amplify the probability, he repeats 4 times the basic algorithm of partial collapse, because now you have 4 branches, each succeeds with probability 1/4, right? So you compensate for the drop in probability of success by repeating the algorithm 4 times. And you keep doing it recursively. And in this way, you amplify the probability to 1 over log n. Log n is crucial in randomized algorithms. Why? Because if you repeat an algorithm that runs that's with probability of success 1 over log n, if you repeat it a multiple of log n squared many times, right? Then this probability of failure, 1 minus log n, taken to the power log n, actually is large because it's 1 over e. Because 1 minus 1 over k to power k is just 1 over e. So if you run your algorithm only log n many times, probability of success will be 1 over e, which is about 1/3, which is not bad, right? But if you run it log n squared, the penalty price is that you have to multiply your runtime, not with log n, but with log n squared. But then the probability becomes e to the exponent that is log n, right? And this becomes 1 over n. So that's another, so the cost is run it log n squared many times. So the cost in runtime is acceptable because the number of repetitions is still log n squared. So the total runtime is n squared log n cube, which is still much better than n to the 4th. So, so if we were to work on algorithms like this, how would we gain the mathematical knowledge required for developing this? Okay, honest with you is, okay, so just like with everything else, when you look, we will be looking through heaps of randomized algorithms, especially those for data science. And even though you will see that the themes repeat. So amplification of probability is just omnipresent. So these estimates of this form are all over the place. So you will, just like as if you are an apprentice in a trade, right? You will, as you master, as you see more and more tricks, you will have more and more machinery to apply, right? So you pick up the skill, and trust me, the amount of tricks that appears is reasonably limited. Okay, every now and then, someone introduces a brand new trick, and this is colossal, and usually new tricks are introduced by mathematicians or statisticians or computer scientists who were trained as mathematicians and statisticians. But there is no need to introduce new technique. In the next topic, namely the PageRank, all that Page and Brim had to know is what a random walk on graph is and what a Markov chain is, and know very few basic properties that you learn in every course, like for example this one, or if you take any probability and statistics course, which I encourage you to do, you hear this basic stuff. So their math knowledge was very rudimentary, but they managed this very basic knowledge to apply in a colossal way. So you don't need to be able to invent a new technique like Karger did, but you can absorb the tricks that these people use and apply them on other problems. And if you understand the algorithm, if the problem is not the same, often you can tweak existing algorithms so that they fit the new problem, providing that you really understand how and why the old algorithm works. So trust me, you don't have to become a mathematician to master design of randomized algorithms. And even if you don't design algorithms, if you understand them, you will be infinitely better in knowing which existing algorithm to use, right? If you just have black boxes, if you treat algorithms as black boxes, you cannot make any adjustments, right? And you don't know exactly what makes them perform good or bad. So, so you see, unlike 3121, that we covered very basic techniques. In this course, you will see very fancy advanced stuff, but it's the stuff that works. And I guarantee you, it's absolutely absorbable by computer scientists. It just takes patience and going step to step. And I can tell you from the questions that you ask, that you are, at least those a few people that ask questions, that you are on top of it, right? So, you know, you cannot do great, you know, if you want to fly to the moon, you cannot make a rocket in your garage, right? Or if you are designing a new amplifier, you have to learn basic circuits, you know, differential amplifiers, cascade, and this and that, right? To then compose a new amplifier that you need. Just as you have basic circuits that you did not invent. there are basic blocks in the construction of algorithms that you don't have to invent, but you can just compose them in new algorithms. And you will see gazillion of examples in this course. So please don't get intimidated. But, you know, this is really, really important stuff, and it's absolutely within your abilities to grasp it very solidly. Okay. So should we revise all the techniques from 3121? I've forgotten a lot of them from not touching them. Okay, so this is the deal. You will revise it as we go through the material and we use them. The main technique is greedy and dynamic programming. Here we used also kind of mentioned max flow, but we really didn't quite use it. So you might want to look again at DP, because quite a few algorithms will use DP. So yeah, so this is Karger mean cut algorithm, and as a good example of probability amplification. Any questions that you might have so far? Okay, so just read carefully, never wait, don't let things accumulate, because all the stuff will be as fancy as what you saw. So it will just go one on top of the other. It will overwhelm you if you don't regularly study. So every time after a lecture, find 2 hours to go carefully with a pen and paper through the algorithm and try. You are now buying the tricks. You are now an apprentice in a trade. Algorithms is essentially simply a trade, right? Like plumbing or electrician or whatever. And in the same way, how you do, learn, you know, any trade, you have a master, in this case, Karger, has to show you the tricks of the trade. And the tricks of the trade are not enumerable. They start repeating pretty quickly, as you will see. So read everything carefully, because we have to go forward and see new stuff. And the next topic will be the page rank. So I'm just going to ask you a few questions so to explain, so that you can understand next week the page rank, right? But this is just for preparation. We will not do anything for today. Karger is a good bite for you. So here is the question. You want to search internet, right? So you have your keywords, and your search engine has a huge database of all sites that contain all or most of the keywords that you typed in. But now the problem is, which websites should it show to you? Because obviously, not all websites are equally important. For example, you know, you can have a Wikipedia article about certain algorithm, or you can have a blog that only mentions this algorithm, or you can have a lecture notes that contains the details of this algorithm. And clearly, if you did mean cut, search for mean cut, the search engine is now facing the problem to decide in what order should it present the websites that contain the keywords. So somehow it has to order the websites according to their importance. How should it decide about importance? Well, you could go to a website and see whose website it is this a reliable person or not? But you have to do it for every website, and they are in trillions, so this obviously will not work. So somehow you need an engine that can automatically, without using any much of artificial intelligence or anything else that is not 100% reliable, it should determine the importance of the websites from parameters that can be automatically obtained just by surfing by a robot, a web, and registering the websites. So how would you tell that a website is important? Well, one might think that an important website is the one for which there are many other web pages that all have a hyperlink to this page P. So you have P1, P2, up to, I don't know, maybe P100, and all of these web pages have hyperlink to page P. So it seems the problem is not that hard. Just sort, just do an automatic search of the web with a robot and sort the web pages according to how often they have links to them. What do you think? Is this a good idea, or does it have a problem, and what problem might it have? Any suggestions? What's the problem of calling a web page important if lots of web pages point to that web page? Here is very good answer. Erwin says, people generating fake websites to boost link counts. Exactly right. If I want my web page to become important, all what I have to do is create automatically, say, a few thousand of bogus web pages whose only content is the link to my web page. And lo and behold, if Google counts the links, voila, I cheated Google into promoting me into importance. So this does not work. How can we improve that? Well, one might say, okay, I will not count just the number of links, but I will also look at how many links the pages that point to my web page themselves have. So if P1 has no link pointing to P1, I will kind of discount the link from P1 to P, because no one thinks P1 is important because no one points to P1. So then maybe we should call a web page important if lots of links point to it, and these links come from web pages that also have lots of links in turn pointing to them. What do you think? Will this solve the problem? If I only count web pages so that lots of other web pages also point to that web page. Couldn't we make, so Zaim says, couldn't you make a complete graph to raise the importance of all the vertices? That's exactly right. So again, what I am going to do, I will simply create 1,000 bogus web pages that will all point to each other and will point also to the web page that I want to promote. So now, lo and behold, every web page is pointed at by many other web pages. So the fact that that web page has a link to my web page would count highly. So this will not work again. And the conclusion from this analysis is that whenever something can be altered by a relatively local action, because you see, all these solutions to rig the importance of web page rely on the fact that maybe there are a few thousand or 10,000 pages involved, but 10,000 pages involved compared to 1 trillion total number of web pages is a very small fraction. So the conclusion is, and that's the brilliant realization of the Google people, that in order to make a system, ranking system, difficult to rig, the rank of each web page should depend on ranks on absolutely all other web pages on the web. Because only then every single person or a group of people can control only a small fraction of the internet, just minuscule fraction of the internet. And if the ranks depend on all other ranks, they will not be able to skew the ranking. So the brilliant idea is PageRank has to be a global feature where the rank of each page depends on the rank of every other web page. And that's the first crucial realization that Google people had, that the ranking has to be a global process taking simultaneously into account all possible or most of the web pages on internet. And this is how this is done. It's quite ingenious, even though all the techniques used were in existence for decades, if not centuries, in fact, centuries before Page and Brim. Namely, they were studied ad nauseum by statisticians and mathematicians, and they are called Markov chains. And the special case is random walks on graphs. So you see, Page and Brim did not invent the wheel. All the wheels are in existence, but in all of the brilliance of these mathematicians and statisticians, no one of them figured out how to use Markov chains to make billions. And this is where the niche for computer scientists is. You should not hope, unless you study mathematics, that you will invent new Markov chains. Most likely, you will be using well-known tools, but you will have a good understanding of computer science problem that mathematicians, I guarantee you, do not have, because they live exclusively in the abstract world of mathematics and very often have no common sense for practical problems. And computer scientists should learn math just to be good enough for all practical purposes. And this is done without becoming a mathematician. So next time you will see the magic of PageRank and how brilliantly it is employed to search the web. Okay, so that's more than enough for today. Please read the Karger mean cut before next week. And next time we are going to enjoy the PageRank. So see you next week. Oh, consultation times. Okay, so my consultations will be on Wednesday, but because I get out of breath by 1 o'clock, I'll make them say from 2 to 3 today. And today we will use the same link, this link for today's lecture. So if you have questions, just log in at 2, and I'll be more than happy to help you with any question that you might have. I hope you are thinking about your projects. Okie dokie, anything else that I can answer for you now? Okie dokie. So you are all most welcome. It's a real pleasure teaching you, so I'll see you next week or on my office hours in an hour.